So first method of preparation we have discussed, that is from halogen acid. The next is preparation of haloalkane from Lucas reagent. Lucas reagent. So what is Lucas reagent? Lucas reagent is 1:1 mixture of ZnCl2 and HCl. The 1:1 mixture of ZnCl2 and HCl is called the Lucas reagent. This reagent gives both type SN2 and SN1 reaction. In SN1 reaction we prefer the 3-degree carbon compound or 2-degree carbon compound, but in SN2 we prefer always 1-degree carbon compound. Okay, so this Lucas reagent is also used for the testing of the alcohols. Okay, see how. If the Lucas reagent in SN1 mechanism, in SN1 reaction, Lucas reagent, it gives rapid product. In 1 degree it gives rapid product in SN1 mechanism. In SN2 mechanism requires, it gives so slow product, and it requires warm with ZnCl2. Okay, so SN1 mechanism gives immediately product or rapid product, but in the case of SN2 reaction we have to warm the reactant with ZnCl2 to get the product. Alright, let's discuss both of them, SN1 and SN2. If we are taking the SN1 reaction, so we have to take the 3-degree carbon, like we are having the 3-degree carbon compound. We will react it with HCl, ZnCl2, that is Lucas reagent, and it will give a product immediately. Cl plus H2. So it will give the product immediately. Okay, so 2-3 things you have to remember. It is also used for the test for the alcohols. Lucas reagents is used for the testing of alcohols. Used for the test of alcohols. Like if you are using a 3-degree carbon compound, it will give, or 3-degree alcohol, it will give the instant, turbidity. What is turbidity? Turbidity means it will react so fast and produce so much smoke. And if you take the 2-degree alcohol, it will take 5 to 10 minutes for turbidity. And if you take 1-degree alcohol, there will be no reaction. So because of this, we use that Lucas reagent for the testing of the alcohols. whether the alcohol is 3 degree, 2 degree or 1 degree. Okay. So this is our second method for the preparation of alcohol. Okay, next one is reaction of alcohol with px3. Okay, in case of px3, reaction of alcohol with px3, that is phosphorus trihalide. Alright. See, whenever we react the alcohol ROH with px3, so it will break in a two part, that is X minus and pH2 plus. Okay, so what will happen here? This oxygen will donate its electron to this compound and X will attack to the R. The product will be XR plus OH, then PXX. Okay. Now, if you take the three compounds, because we are having the three halogen compounds, so it will react again. Okay. It will react again from this compound, and finally we will get the product, that is 3R product is there, so we will get 3RX plus, like this, H, this is PX. So it will form H3, 3H is there, PO3. Okay, so this is what you will get the product, H3, 3RX, H3, PO3. Okay, and it will form, because 3R is there, so 3RX and H3, PO3. Okay, so this will be your product. Now, in the case of PX5, okay, you can take example of PCl3 here, or here PCl5, that is pentachloride or pentahalide. When we react the alcohol with pentahalides, ROH plus, so this pentahalide will break in the form of X and PX4 plus and X minus. Again, oxygen will donate its electron to phosphorus and X will attack to the R. The product will form again RX plus OH and phosphorus 4. 1, 2, 3, 4. Halogen is there. Okay. Now, one thing you have to remember here: two halogen compounds are at horizontal position, so both are unstable. So one H will take the X and remove from the compound, so it will form a HX. So the final product will be RX plus HX plus POX3. So this will be the product in the case of PCl5. Okay. Okay. Third method is the case of thionine fluoride, that is SOCl2, or thionine bromide, that is SOBr. See, this is called the most effective method to produce the haloalkane. Most effective method. This is the most effective method to produce to produce haloalkanes. How? When we react the alcohol ROH with SOCl2, okay, it will form RCl with SO2 and HCl gas, and the both gases are escapable gases. Both are the escapable gases, means these gases are escaped after the product is formed. So we will get the pure haloalkane in a product side, and the byproduct gases will escape from the product. That is why this method is called the best method for the preparation of haloalkane. Okay. So next preparation method is from hydrocarbon. From hydrocarbon. First is by direct halogenation. Direct halogenation. Okay. See. If we react the hydrocarbon with the halogen in the presence of sunlight, heat, or any other catalyst, it will form a haloalkane. Okay. So when we react the hydrocarbon with halogen in the presence of sunlight, heat, or catalyst, it forms haloalkane. See here what happens when you took chlorine to react with the hydrocarbon. So fluorine is very reactive gas, so the reaction becomes explosive. So we don't use fluorine. If we use chlorine, it gives a fast reaction. If you took bromine, it will give you a slow reaction. But in case of if you are using the iodine, so iodine will produce Hi, or in the case of iodine, when you react the iodine with hydrocarbon, you have to use oxidizing agent. You have to use oxidizing agent like HNO3 or HiO3 to reduce the Hi so that we can form the product. So let's understand one by one. If we take the hydrocarbon methane and react it with chlorine, so what will happen here? It will follows a free radical mechanism in the presence of sunlight. So we are having a methane. Methane means 4 hydrogens are there, and here we are having the chlorine. So it will follow a free radical mechanism, means the hydrogen will break from here, taking its own electron, and both chlorine will take its own electron and break from each other. Now, this Cl will attach with the H and form HCl, and this Cl will attach with the carbon and it will form methyl chloride. So you will get the product like this. Now, in case of you are having a compound CH3, CH2, CH3 and react it with chlorine Cl2 in the presence of sunlight. At this case, you will get the two products. Okay, you will get a two product because Cl can attach to the any carbon, irrespective of their position. It is able to attach with any carbon. So if it attach with the intermediate carbon, it will form a product like CH3, CH, Cl, CH3, or if it attach to the terminal carbon, it will form product CH3, CH, CH2, Cl. So both kind of product are formed in this case. Okay. Now, when you react it with the iodine, in the case of iodine, what happened? Like if you react the hydrocarbon with iodine, like you are having a hydrocarbon CH4 and we are reacting with iodine in the presence of sunlight. So it will form CH3I plus Hi. So Hi is a reducing agent. So because of reducing nature, it will again form the reactant, that is CH4 and I. So it will again release the H and this H will combine with here and it will form again CH4. Means the reaction will take place in the reverse direction. Okay. At this condition, we have to use a strong reducing agent like HNO3. This HNO3 will react with Hi and it will form. So if we use HNO3, CH4 plus I2 in the presence of strong oxidizing agent. Okay. So it will form CHI3 and in case of Hi, it will form a reducing agent. Reducing agent, what reducing agent it will form? It will form a NO2 and H2O. NO2 and NO2 and OH H2O. Plus I. So in that case, Hi is not formed. So now iodine is get separated. So it is not possible to that it can reverse in the back side. That the iodine again react with the CH3 and it again form with the CH4 and I2. In the case of In the case of in absence of the oxidizing agent Hi, which is a strong reducing agent, it tries to give its H, है ना? Because it is a reducing agent, it will try to reduce the other element, so it will give H to this compound. So this CH3 will again attach with the hydrogen, again it will form the CH4. But in the case of if we use the strong oxidizing agent, this strong oxidizing agent will snatch the hydrogen of Hi, and I2 will be separated from the H. So it is not possible again to form the reactant product. As we have seen here, when we react the hydrocarbon that is CH4, we are not able to react that hydrocarbon from fluorine directly, and also we are not able to react this hydrocarbon from iodine. For reacting with iodine, we have to use the strong oxidizing agent. In that case, we use the halogen exchange method. Okay, halogen exchange method. Halogen exchange method. In this method, we see two types of reactions are there. First one is Finkelstein reaction, Schwarz reaction, and Finkelstein reaction. First one is Schwarz reaction. In Schwarz reaction, we see that we are not able to react the CH4 with fluorine because it is a very explosive reaction. And if we react the CH4 with Br2, it is a very slow reaction. It will form methyl bromide, okay, plus HBr. Okay. Now, if we react this methyl bromide CH3Br with silver fluoride AgF. Now this silver fluoride have the covalent bond. Covalent bonds gives the slow reaction. Covalent bond gives the slower reaction means the bond between the silver and fluorine will break slowly. So silver is not available to react fast. So now the reaction will process in a slow manner. Now the fluorine will react with silver bromide and it will form CH3F plus AgBr. Now, so in this case we can react with the fluorine. Okay, so this is called the halogen exchange method. Okay, this is our Schwarz reaction. One more reaction is there, that is Finkelstein reaction. Second is Finkelstein reaction. Now, in Finkelstein reaction, we react the haloalkane, that is RX. We react this methyl bromide with sodium iodide. Now it will form CH3I methyl iodide plus NABR. Now this NABR forms precipitate, that is PPT, and it will get separated and we will form a product methyl iodide. As we know, directly when we are going to react with the CH4 plus I2, it forms Hi, and that Hi process the reverse reaction. But in this case, no Hi is formed. That is why it is the best method to prepare for methyl iodide. and this is best method for prepare for methyl chloride. Okay, so that is why these halogen exchange methods are used for preparing the haloalkanes containing iodine and fluorine. Okay, next is reaction of halogen acids from alkenes. So next method is from alkenes, alkenes, from alkenes. So when we react the halogen acids, halogen acids, halogen acids means HCl, HBr, HI. So alkenes radially react with halogen acid and forms haloalkanes. Halo, haloalkanes. Haloalkanes. See how? If you are having alkane, that is alkene CH double bond CH2 double bond and react with halogen acids, that is HBr or HCl. Okay. Now the pi electron will shift. If it shift to this side, the positive charge will develop here, negative charge will develop here. Now this Cl minus will get attached to the positive side and you will get the product CH2, Cl and CH. So this is the case of symmetric alkenes. Okay. But in the case of asymmetric alkenes, like if you are having a compound like this CH3, CH2, double bond, CH2, CH double bond, CH2. Okay. Now react with HCl, H plus Cl minus. Now the question is, which carbon will develop a positive charge and which carbon will develop a negative charge, because the pi electron will shift. So always remember, this is your 2 degree carbon and this is your 1 degree carbon. So here we use the Markovnikov rule. What is Markovnikov rule? So write the Markovnikov rule. Markovnikov rule. According to the Markovnikov, 3 degree and 2 degree alkyl halides are preferred over 1 degree because 2 degree and 3 degree are more forms more stable carbocation. So see, one major thing you have to remember, that in alkene 2 degree alkyl halides are preferred. 2 degree or 3 degree alkyl halides are preferred. It means the Cl must be attached with the 2 degree carbon. Okay, so it will attach to the 2 degree carbon. So the electron will shift here, it will form a positive charge, it will form a negative charge. So Cl will get attached with the 2 degree carbon, so it will form CH3, then C, it will get attached Cl, CH, and this will form CH. Now H will attach to this carbon. So this is the according to the Markovnikov rule. According to the Markovnikov rule, 2 degree or 3 degree halides are preferred. That is why the halogen substituent is always get attached with the 2 degree or 3 degree carbon. Okay. At the same time, if there are in the presence of in the in the presence of heat, light, in the presence of heat, light, peroxide, peroxide, in the presence of heat, light, peroxide, the alkene reaction follows the anti-Markovnikov rule, anti-Markovnikov's rule, that is 1 degree alkyl halide is formed. 1 degree alkyl halide which is unstable is formed. So in the same case, if we use peroxide in the same reaction, like we are having an asymmetric carbon CH3 CH double bond CH2 and reacting with HBr in the presence of peroxide. Now the reaction will follows the anti-Markovnikov rule. Will now the Br will get attached to the 1 degree carbon, not the 2 degree carbon, and forms a 1 degree halide. So the product will form, that is CH3 CH CH2 Br plus this value. So hydrogen will get attached here, CH2 and this CH2. So this is the anti-Markovnikov's addition. So anti-Markovnikov addition will take place only in the case of when in the presence of peroxide, heat and light. Alright. Now I have written some examples in the left side. Let's solve that example. See, first CH3 CH double bond CH2 HBr. It will follow the Markovnikov's rule, MKR Markovnikov's rule. So the product will be Br will get attached to the 2 degree carbon. So our final product will be CH3 CH Br and CH3 and H will attach to this carbon. Next, in the presence of peroxide, it will follow the anti-Markovnikov rule. So our final product will be CH3 CH2 CH2 Br. Now Br will get attached to 1 degree carbon and H will attach to another. Here also anti-Markovnikov rule will be followed. So here you can see this is your 2 degree carbon and this is 1 degree carbon. So Br will get attached with the 1 degree carbon. Our final product will be CH3, C, CH3, this CH2. So H will attach here and Br will attach here. Here also anti-Markovnikov rule will be followed. See, this carbon is a 3-degree carbon and this carbon is a 2-degree carbon. Okay. So because anti-Markovnikov rule, Br will get attached with the 2-degree carbon. So our product will be, where you will get Br and this will be C, and H will attach to this carbon. So this is how we apply the Markovnikov rule and anti-Markovnikov rule. Okay. Okay. Next is addition of halogen. Addition of halogen. See, when you take the alkene, that is CH2 double bond CH2, and react it with bromine in the presence of nickel, platinum, palladium. So what happens? Bromine will get combined with the alkene. Normally the color of bromine is brown. After the combining with alkene, it will form a reddish brown color. It will form a reddish brown color. Because of that, it is also used for the test of the unsaturated compounds. Used for testing unsaturated carbon compounds. Okay, that is why it is also used for testing the unsaturated carbon compounds. So this is the addition of halogen. So whenever we react the bromine with the unsaturated carbon compound, that is alkene, in the presence of CCl4, it gives a reddish brown product. It confirms the presence of unsaturated carbon compound. Okay, so this is all about the preparation of haloalkanes, and in the next part we will discuss the preparation of haloarenes. Okay.